All right, everyone. At long last, we're going to go ahead and finish up Unit 3.12? Yeah, Day 4. Ugh. We saved the most interesting for last. Let's say it like that. What have we been doing? We have been using trig identities to solve trig equations. Here we use the double angle identity, so that way we could write this polynomial in one form of trig. Here we used a double angle identity that, even though we didn't get only one kind of trig, because your goal, if you can, is to have one kind of trig in a polynomial. But sometimes you can't help it, like this one. But once we got to here, we were in a good place because it factors when it's set equal to 0. So still doable. Here, we created a double angle identity just so we could do the domain stretch thing. So you've seen a lot of double angle identities, and be on the lookout for Pythagorean identities and things like that. Now, I'd like us to take a peekaboo at this question. And notice there's no double angles. So we're not using a double angle identity. You know what else we don't have? Squared trig. And since there's no squared trig, we have no Pythagorean identities to work with. But this can be done by hand. You'll have to pardon the saying because it is, carries a lot more weight in this day and age than it used to. But the saying goes like this, gun to your head, you have to try something. What would you at least try? Because here's the thing. Worst case scenario, you try something and it didn't help you. So then you just try something else. It's not a big deal. You're not penalized for trying and being wrong. So you have absolutely no choice. I'm going to go around with the small bat busting kneecaps unless you try. Somebody tell me something you would at least try to do. Okay, Nyla, what would you try? Let's say we move that trig to the other side. And she says just to see what it looks like. And to be honest with you, sometimes just to see what it looks like this was last class period. Sometimes just to see what it looks like is helpful because maybe it sparks something in your mind. Let's move this cosine x over since it's negative. If we added it to both sides, I would get this. Did it spark anything for you? Part of the Pythagorean identity? Yeah, I mean, this is part of that, right? If we multiplied by the conjugate on both sides, we would have a Pythagorean identity right here, right? Let's see what that would have looked like if we tried. Multiply both sides by the way, nobody said this in second period, so I have no idea what this is going to look like. On the left side, do you want to distribute it? I'll distribute it. On the left side, it gives me sine x minus sine x cosine x. On the right side, I'd have 1 minus cosine squared x, which is sine x, sine squared x. She says subtract it back over. All right, I mean, if we subtract it back over, we've got and unfortunately it won't factor because this has a cosine x hanging out in it. If you try to take out the GCF would be sine x. Let's see. And I don't know if you realized, but that right there is that right there. So we found ourselves some circular logic that got us nowhere, but at least we tried. All right. That was fun. So moving the trig around Didn't do us any good. Sometimes that happens. What else can we try? What else could you try to do, Mark?
Maybe replace the negative before the cosine into cosine negative x.
Say that again? Oh, he says because cosine is, no, what you're thinking, that only works for odd. Cosine of negative x equals cosine of x. He was trying to use an even odd identity. Here's what, we don't want to try to do that because if we have different arguments in our trigonometry, it'll be almost impossible to solve. But good thinking, but it won't work for this one. I'm just going to wait until someone comes up with it. Maybe if Jack was on his phone, maybe he could come up with an idea. You could square both sides. If you square this side, we're going to end up with squared trig, aren't we?
Yeah.
And squared trig might be useful to us because of Pythagorean identities.
Yeah. I know that's a legal move or not.
Well, of course, I mean, you're allowed to square both sides of an equation, aren't you? It's just like taking the square root of both sides. Why not? And that's actually how we do this question. Luckily, 1 squared is 1. I'm going to have to trust that everybody in the room could FOIL and combine like terms. And at first glance, it looks like we made it uglier. But what do those two things add up to? 1. That is the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Now what? Subtract the 1 from both sides. This is a double angle identity. Sure is. But you know what? You're going to make the question harder if you use it. Because you have the product of two things equals 0. It's as if you factored something and set the parts equal to 0. The only way the product is equal to 0 is if the parts equal 0. So yeah, this is a double angle identity, and you could divide both sides by the -1 because it's that's sine of 2x, right? But then in order to solve the sine of 2x equals 0 thing, you would have to make a substitution for the argument and do that whole domain stretch deal. When you could just say either sine of x is 0 or cosine of x is 0. That's actually easier. I know that for a fact because in period 2, we did use the double angle identity and then went through the domain stretch. But that kind of sucks. So I would just say divide both sides by -2 and get to sine x times cosine x equals 0. Because that is going to guarantee us that either sine of x is 0 or cosine of x is equal to 0. It's as if we solved by factoring. And now we just get to ask ourselves, where does that occur? In the first full circle, when is sine 0? 0 and pi. 0 pi and 2 pi, but we can't count 2 pi. And the reason why is because when you're on the x-axis of the unit circle, there is no y value, so sine is 0 over r. So we have results of x equals 0 and x equals pi. When is cosine of x 0? The y-axis, when there is no x value, so pi over 2 and 3 pi over 2. So it certainly looks like there's 4 answers, doesn't there? There's not. But why? we created extraneous solutions when we squared both sides. Well, we created the opportunity for extraneous solutions. Because what do squares hide? Negatives. Squares hide negative values from us. When you squared both sides, you allowed this left side to have a value of 1 or negative 1. Because if you square a 1 or a negative 1, you get back a positive 1. So it doesn't guarantee you have extraneous, but it opens the door for it. Remember that. When you square both sides, you have created the opportunity for extraneous solutions because you just made it so that there's no such thing as negatives. So we have to actually test our answers to make sure they work. Back to the beginning. Sine of 0 is 0. What is cosine of 0? 1. So this says negative 1 equals 1. X equals 0 is extraneous. It tells us negative 1 equals 1. Then we test pi. Sine of pi is 0. Okay. What's cosine of pi? Negative 1. So this says negative negative 1, which is positive 1 equals positive 1. Pi works. Let's try pi over 2. Sine of pi over 2 is 1. What's cosine of pi over 2? 0. So at pi over 2, it says 1 minus 0 equals 1. We're in good shape. And lastly, 3 pi over 2. I keep pointing at this here. At 3 pi over 2, what is sine's value? Negative 1. What is cosine of 3 pi over 2? 0. This says negative 1 equals 1. So there are only two solutions, pi and 3 pi over 2. It's because we squared both sides. So Nyla, you said you weren't sure if that was a legal move. Yes, it is legal. But you have to make sure at the end that the answers worked. Because squaring both sides instantly hid every negative result from you. All right. Another way to do this question? No, not that I know of. I mean, there's other ways, but they just create more work. For example, if you really wanted to, you could have, and it wouldn't be helpful at all, but you could have divided everything by cosine of x. And you would have gotten tangent x minus 1 equals secant x, which doesn't really help you all that much. But you could then square both sides and maybe create some Pythagorean identity somewhere. But it just ends up running in a circle. Also, you have to be very careful with dividing by functions. If you divide by a function that has the ability to equal 0, you just divide it by 0, which you're not allowed to do. And since cosine of x does equal 0 in this domain, dividing by 0 would be, or dividing by cosine of x would be dangerous. Now, you can get away with it as long as you're not canceling it. So like if, let's just say this equaled 0, and I was like, oh, I'll just divide everything by cosine, and because I'll get a, no, that's dangerous. Dividing by cosine to create tangent, that is admissible, but you still have to make sure to watch out for extraneous solutions, because maybe you divided by 0, you know? In essence, don't divide by a function unless you know for a fact it's never 0.
Like if domain restriction applies?
Yeah, like if there was a domain restriction, or like you could divide by e to the x all day long, because e to the x is always positive. You know, it's things like that. So yeah, if you have a function that either through domain restrictions or just by its very nature is never 0, divide by it all you want, no big deal, you know. And this last question. I'm not gonna lie. In second period, we did it a really hard way. And can you take a guess at what that really hard way was? No. What? No, what were you saying? If you square both sides, like we did here. And that's how we did it. And it works. And we got to the right answers. But it was more work than I want to do. And I tried it a secondary way. And I actually tried what I just said to you. I divided everything by cosine x. So I could get a tangent here and a secant here. And then I attempted squaring to get Pythagorean identities. And no, it was horrific. It was bad. It didn't make it any easier. So we are going to end up squaring both sides. But we're not going to do it here. Because squaring this mess is nowhere near as easy and clean as squaring that. So we're going to clean it up first by adding that to both sides. Now squaring both sides won't be so bad. But we do have to remember that the moment we squared both sides, we hid negative things from ourselves. We've now just said that -1 equals +1 works. And we know that that's a no-no. So at the very end, we will have to double check our solutions to make sure we haven't done anything that creates extraneous solutions. To make sure we haven't, gotten any false statements. Yes? How would you know? You wouldn't. You, like trig proofs, you kind of have to just be willing to try. And if it doesn't work out, don't despair. Just go, okay, that didn't work out. And toss it and try something else. I mean, where's my work? Where was I? Here's me attempting to do it by dividing everything by cosine first. And then attempting to square it. And no, I mean, look, it just go, woo, it was bad. So I said, okay, no good. And I tossed it, And here's us in second period squaring both sides. I mean, look how much work it was. So how do I know that that was not the best way? Because when I did it, it just felt like it was too much work. Does that make sense to say? Like, I just felt like there must have been a better way. So I looked up the official way it's done. And I was like, oh yeah, okay, that way is better. But it's just like trig proofs. Just because a way is better doesn't make it correct. It just means that it was the better way. It was more efficient. And so did I know to move this over to make it more efficient? No. I mean, the dead giveaway should have been, why would I want to bother squaring that? I knew for a fact I was going to have to square both sides because there's no squared trig. Basically, there's no squared trig and there's no double angles. You don't have a choice. You're going to end up squaring something when you have multiple kinds of trigonometry, And I should have seen that squaring this would have been better because if you square this, you'll never have a sine x times cosine x anywhere. Where if you square that, you will. See? I mean, to be real with you, if we moved that over and squared both sides, bless you, we would never have had this sine x cosine x. I don't know. Maybe after we do this one, maybe we come back to this one, move the cosine x and square both sides and see if it was any easier or harder. I mean, there's no reason in not doing it, Basically, you don't know. Doing lots and lots and lots of practice tells you maybe that'll be easier, maybe that won't be. Who knows? I'm not going to lie. A minute ago, I was kind of hoping that was going to be elegant. I was kind of hoping that you guys were onto something. And unfortunately, it wasn't. But it was interesting, at least, Okay, we have sine squared x just like I said last time, I'm going to have to hope that you know how to FOIL and combine like terms. Root 3 times root 3 is 3. So it gives me 3 cosine squared x plus 2 root 3 cosine x plus 1. Well, if we factor this, we get this back. And you don't ever want to solve by factoring unless it equals 0. Okay? It's kind of annoying that there's two kinds of trig, isn't it? Downright annoying. Wait, Ashley, what? Yeah. Something. It equals 1 minus cosine squared x. And if you subtract the 1 from both sides and add the cosine squared x, what you get is this. So we're adding a cosine squared x. And the 1s are gone. Turder. How do we solve that? What? You can factor. What is the GCF? 2 cosine x. And there we go. What we get is that 2 cosine x is 0, or this thing is 0. So either cosine x is 0, or subtract root 3 divided by 2, cosine x is negative root 3 over 2. So much less work than what we did in period 2. When is cosine 0? The y-axis. Pi over 2 and 3 pi over 2. Good. So we have x equals pi over 2 and 3 pi over 2. And for this one, I'm going to need to draw. Cosine is negative in 2 quadrants. I don't know when those happen, so I'm going to go ahead and draw it because I don't have my unit circle memorized. But I do know that cosine is x over r. So negative root 3 over 2. That makes these 1s. Oh, those are pi over 6s, aren't they? This one is 5 pi over 6, and the other one? 7 pi over 6. And lastly, because we squared both sides, we open the door for extraneous solutions where negative 1 equals positive 1 without knowing that it happened, so it's time to test. Here's the good news. We know for both of these answers, cosine is 0, right? So it's actually pretty easy to check. So we know that when we plug pi over 2 in, this is gone. Is sine of pi over 2 1? Only one person answered. Is sine of pi over 2 1? Yes, it is. Is sine of 3 pi over 2 1? No, it's not. It's negative 1. Okay. Good news. When we plug both these in, we know that this cosine equals that. And what is negative root 3 times negative root 3 over 2? Positive. 3 over 2. So we know that when we plug in both of these, this becomes plus 3 over 2, right? Okay. So plus 3 over 2. Sine here. Is sine positive or negative? Positive. Positive number plus 3 over 2 equal to 1? 3 over 2 is bigger than 1. So positive number plus 1.5 definitely isn't equal to 1. Whereas here, sine is negative. Negative 1/2. Negative 1/2 plus 1.5. Yes. So those are your two solutions. And there it is. Now, out of curiosity, because why not? Need to find me some more scrap paper, because I want to try that other question now. I want to try this one and see what happens if we move it all to one, if we move the cosine and then square. Because maybe it's easy. Who knows? Or maybe it's worse. Who knows? It's all about not being afraid to try. So let's add cosine x to both sides. Now let's square both sides. If you square both sides, you get sine squared x equals cosine squared x plus 2 cosine x plus 1. This is 1 minus cosine squared x. The 1's cancel. And if you add, you get 2 cosine squared x plus 2 cosine x. I think that was even easier. Look at that. Where's cosine x 0? Where's cosine x negative 1? Cosine of x is 0 at pi over 2 and 3 pi over 2. Cosine of x is negative 1 at pi. That only gave us 3 solutions, whereas when we did it this way, we got 4 solutions. You'd still have to check for extraneous. That's crazy. That this one developed 3 answers, and this one gave me 4. The 3 pi over 2 is still not going to work, you know, because sine 3 pi over 2 is negative 1. So this says negative 1 equals positive 1. But I think it was less work. It was less work, and we used a single Pythagorean identity. I don't know, maybe it wasn't less work. Maybe it's about the same amount of work. But you see, done a completely different way, and we get the same answer. Just goes to show you. I honestly do think that one of the major differences between people that are highly intelligent and those that are not are those, I think that highly intelligent people are not afraid to experiment and be wrong. So if that's what makes me a nerd, because I'm not afraid of trying and being wrong, so be it. I don't care.